Okay, we have a live stream, Arsh. We have a live stream, Arsh.
Yeah, I can see it on YouTube. It's just like a several second delay.
Yes.
Yeah, I can see it on YouTube. It's just like a several second delay.
Yes. All right. All right. Let's go ahead and get started. Welcome, everybody. I'm Shalini DeMello, and I'm a principal research scientist at NVIDIA. And this is the ECCV2020 tutorial on the new frontiers for learning with limited labels or data. And I'd like to welcome you today from where.
Let's go ahead and get started.
Sorry.
Welcome, everybody. I'm Shalini DeMello, and I'm a principal research scientist at NVIDIA. And this is the ECCV2020 tutorial on the new frontiers for learning with limited labels or data.
Do you?
I'd like to welcome you today from where.
I think you need to close the YouTube stream
I see.
or actually mute it somewhere. I think
see.
you're probably
Sure.
opened both.
I see. Okay. So I quit out of Chrome. So let's give this another try. Thank you, Varun. All right. Let's give it another try. Welcome, everybody. This is the ECCV 2020 tutorial on the new frontiers for learning with limited labels or data. And my name is Shalini DeMello, and I'm a principal research scientist at NVIDIA. And today, we're very excited for you to join this tutorial from wherever in the world you might be. And we're very excited to share this topic with you and share our excitement and all the interesting new work that is being done in this area. And just, I'm going to go very briefly through some thoughts. And recently, Jan LeCun famously said, the AI revolution will not be supervised. And we couldn't agree more with him. And the reasons are that obviously collecting large amounts of data and annotating it is very costly. And I feel that for the long run, for the sustainability of AI, this is something that is just not sustainable as a process. And also it prevents democratization of AI technology to communities and societies where it's just not feasible for them to collect such data at such large scales. And after a point, data, if you keep collecting the same kind of data, it becomes redundant and there's diminishing returns in terms of how much it improves your model. And as a researcher, purely from a scientific perspective, there's always this curious question of, well, humans can do it, and they're very good at learning from imperfect or little data. And so why is it that, what is it lacking in AI algorithms that prevents them from being able to do this? And recently there's been a lot of research in weekly, semi-supervised, zero-shot, few-shot learning, et cetera, which is really great, and it's a step in the right direction. But in this tutorial, we wanted to sort of introduce you to some new frontiers and some new exciting ideas that are emerging beyond sort of what has been studied in the literature of learning with limited labels or data. And specifically, we're going to focus on three main topics in this tutorial. The first of which is on self-supervised learning. And we'll have two great talks today. The first by Varun Jampani and the second one by Sifei Liu on learning various attributes from image collections without labels in a self-supervised manner, and also leveraging correspondence across instances and across videos to learn attributes and properties across videos for various different computer vision tasks. And then we're going to have another talk today, which is on learning with imperfect labels, and in particular, noisy labels by Arash Wadat. And so we will cover, of the total 6 talks in this tutorial, we're going to cover 3 today in this session, which is a 1.5-hour session. And then the remaining 3 talks, which will be on learning with imperfect labels with visual data, and also 2 talks on inverting neural networks, and the other one inspired by biological neurons, will happen tomorrow in tomorrow's 1.5-hour session, which will be at 6:30 a.m. Pacific Standard Time. So wherever in the world you might be, you would have to convert it to your time zone. And lastly, I just wanted to point out that we have a website where the recordings of all these talks that were pre-recorded by the presenters are also available. The PDFs are available as well, and you can reach out to us, for example, on Twitter. And with that, I would like to hand it over to Varun, who will be presenting the first talk. And Varun is a researcher at Google. He's interested in many fundamental problems related to computer vision and machine learning. And he's going to describe very exciting work on self-supervised learning of attributes. Take it away, Varun.
Yeah, thanks, Shalini. Let's share the screen. You can see my screen, right?
Yes.
Yeah. Hello, everyone. Welcome to the tutorial. I'm Varun Jampani from Google Research. Today, I will be talking about self-supervised part and viewpoint discovery from image collections. So what are image collections? Image collections are set of images with common object of interest, common object category of interest. For example, here I have shown here a couple of examples. One is car image collection with images of cars, or face image collection with images of faces. So image collections are quite common in our daily lives. Some examples include image search results, photo collections, or tourist photos of a particular landmark, etc., where we see the repeated photos of same object category. So the basic research question we want to address is that, like, how can we do self-supervised learning of object properties from image collections? By object properties, I mean, like, it could be geometric properties, let's say 3D shape, 3D viewpoint, etc. Or it could be semantic properties, let's say key points, part segmentation, bounding boxes, etc. Or it could be material properties of an object, let's say diffuse albedo, specularities, roughness, etc. So in this talk, I will be talking mostly about this 3D viewpoint and part segmentation. How can we learn this in a self-supervised way from image collections? So the first part of the talk is mostly on this CVPR19 paper, which is self-supervised co-part segmentation. And here the aim is to learn part segmentation from image collections. Here I have shown some sample result from our technique. Given an image collection of, let's say, faces or birds or, let's say, horses, can we automatically discover consistent part segmentations across images? I mean, since they are self-supervisedly learned, they may not have exact meaning as we humans label, but the idea here is that we should be able to find parts that are consistent across different instances. So why parts? I mean, why do we care about parts? Because parts are relatively stable with respect to object deformations. Like, for example, when some articulated object, let's say humans, move, the part shape remains unstable, remains stable. And they provide that's how they can provide reliable mid-level correspondences between images and across video frames thing. And they're also useful for several high-level vision tasks such as fine grained recognition, detection, pose estimation, or 3D reconstruction. So once we have a self-supervised technique to discover parts, this could be useful for several different vision tasks. So in the past few years, there have been several recent works on self-supervised key point discovery. Here I have shown some snapshot of works. There are several other works. On the left is a key point net, which tries to learn 3D key points in a self-supervised way by using multi-view data. And in the middle is a descriptor vector exchange technique that leverage image collections to learn key points in a self-supervised manner. And on the right, it is a recent technique that leverages unlabeled videos and also unlabeled pose data. I mean, the unpaired pose data to learn meaningful landmarks in a self-supervised way from images. But there's some fundamental difference between key points and part segmentation. The part segmentation provides both localization and segmentation of parts, like, whereas key points provide only the localization of some points in an image. And here I have just shown some sample example annotations from different data sets. And part segmentations also can represent these joint regions as a single part. For example, in an image shown in the left here, for example, two eyebrows can be represented as a single part, whereas it is not possible to represent both eyebrows as a single key point with key point representation. So there are some fundamental difference between That's why there's fundamental difference between part segmentation and key points. In this work, we are mainly interested in discovering part segmentations. So there hasn't been much works in part discovery from image collection. This is one of the few works uh, that exist at that time. And so here the technique is quite simple, but they should need to be quite effective. For example, here they pass a set of image collections, let's say here images of Statue of Liberty, to a standard ImageNet classification feature to get ImageNet classification features, which is a fixed pre-trained CNN, and to get the features at each pixel in all the images. And then they concatenate all the features from all the images to make this big matrix A. Here is the number of pixels times number of feature dimensions this matrix dimension is. And then they run simple non-negative matrix factorization to get these H and W matrices. And what they find is that this H matrix automatically gives you some part segmentations, consistent part segmentations across images. And this is a very neat insight that this shows that actually the part segments automatically emerge, or automatically they are hidden part segments, part clusters inside classification train networks, classification train features. So, but there are some drawbacks of this work. Like, for example, it is difficult to scale this to large data sets since you have to make this large matrix. And it's not, I mean, there could be some online techniques to do this factorization, but it's difficult to scale. And it is also not easy to apply to other constraints like part segmentation constraints on this. Yeah. So shall I answer questions later or probably later, right?
Yes. So all of you who are watching, what we will do is at the end of Arun's talk and each speaker's talk, we will reserve some time and answer all your questions. But feel free to put them in the chat as you have them, but we will try to answer them in the end. Thank you.
Yeah, thanks. So we leverage different properties. We call our framework SCOPS. It's a self-supervised co-part segmentation. So we leverage different properties of part segmentation as self-supervised constraints to learn this part segmentation network. Our network takes single image as input and produces part segmentations like this. And we learn this part segmentation in self-supervised constraints. Specifically, we have three different constraints. One is geometric concentration, equivariance, and semantic consistency constraints. In addition, we also learn the semantic part basis, which I will explain in a bit. This geometric concentration constraint is a simple constraint which says that the parts are usually locally concentrated, like in parts should not should not be all over the place in an image. And so we implement this in a very simple way, like we compute, once we get the part segmentations from the network, we compute the centroid for each part. And then we enforce in the loss function that there's all the pixels belonging to that part should be close to that centroid. So this is where we're saying that like the part should be locally concentrated. And the second constraint, equivariance constraint, which is inspired from key point works, is first we pass a given images into with some spatial transform and color jittering to get some augmented images. And then we pass both these original images and transformed images through part segmentation network to get the part segmentation maps. So this equivariance constraint says that both these outputs, so part segmentations for the original images and part segmentations for the transformed images, should conform to each other with respect to the spatial transform. And there are a couple of sample results with and without equivariance. As you can see, with equivariance constraints, you can get much better consistent parts across images compared to without equivariance constraint. A third and most important constraint in our framework is the semantic consistency constraints. Here, let's say these are the image collections during training, and we first pass these through a pre-trained ImageNet classification network to get classification features. Here, we additionally pass these through a saliency constraint through some unsupervised saliency, using some unsupervised saliency work, and so that we only get features mostly on the foreground regions, this here. And we also pass the same set of images through our part segmentation network to get part segmentations. In addition, we also learn the part basis. Let's say we are learning 5 parts and we have this 5 part basis for each part, these part features for each part. And then we multiply these part bases with our part segmentation network to get a feature map. So what this multiplication does is that like it actually puts each of the part, let's say if it is a part one feature, it actually puts part one in the part in those pixels where the network predicts those pixels as part one. So it is just spreading all these features into part bases uh, into these image pixels where the network thinks those parts are detected. So then we say that like this feature map should be similar to the feature map that we get when pre-trained classification features. So as you can see, this is kind of like inspired from the previous work, deep feature factorization, but instead of doing optimization, we actually do this in a more feed forward manner where we actually also learn these part bases from scratch. So one of the issues that one could face here is that like these part bases can collapse to smaller number of part bases. So in order to avoid that, we also add this orthonormal constraint, which says that this part should be orthogonal to each other, should be as different to each other as possible. So here is a sample result without semantic consistency and with semantic consistency. And as you can see with semantic consistency, you get the regions more concentrated in the foreground. This is mainly due to saliency constraint. And also the parts are more semantically meaningful, which is coming from these learned part basis thing. So here is a sample result that is shown, sample part segmentation shown during training. As you can see, the part segmentation gets better and better during the iterations, training iterations. And in the bottom, I have shown these TSNE plots. For each part segment, we have taken the ImageNet features and plotted two-dimensional TSNE plots. As you can see, the part features gets more and more clustered as the training progresses, which is what we expect. And we evaluated this part segmentation on this unaligned Salabia dataset. And here, as you can see, compared to previous unsupervised landmark detection and deep feature factorization techniques, we get uh, much better consistent parts and meaningful parts. And also in terms of landmark estimation error, we outperform these two previous techniques. And this is also, we have experimented on CUB dataset, bird dataset, fine-grained bird dataset, and where again, we get better parts compared to previous techniques. And here is a result on Pascal parts dataset and on horses. Again, here we can observe better consistent parts across images using SCOPS technique. And here are some results on other Pascal parts categories. So as you can see, the parts are far from perfect and there is a lot of scope for improvement, and these objects are quite challenging to find some consistent parts. So that is about SCOPS, and there is some recent follow-up work from some other group, which is motion supervised copart segmentation, and where they leverage video frames to improve SCOPS and by enforcing consistency across video frames thing. And they get better consistent parts across video frames compared to SCOPS. And also in our follow-up work, we also use this SCOPS part segmentation to actually learn 3D reconstruction of objects from image collections in a self-supervised way. Next, C-File will talk about this work in detail. So in summary, I've talked about a couple of works such as on the part discovery with self-supervised constraints, and the main aim is to avoid degenerate solutions when trying to discover part segments. So we do this by leveraging part properties such as equivariance and geometric concentration, and we also leverage hidden consistencies in classification features in terms of semantic consistency loss. So we find these discovered part segmentations are useful for several high-level vision tasks such as self-supervised object reconstruction. And there is a first part of my talk, and in the second part, I will talk about self-supervised viewpoint learning from image collections, which appeared in CVPR 2020. So viewpoint annotation is hard because we need to align 3D models to 2D images to align 3D viewpoint for images. And it is time consuming, expensive, and it is error prone. So that's why it would be useful to learn, actually able to learn a viewpoint So we aim to learn a viewpoint network that takes images input and predict three angles, azimuth, elevation, and tilt angles, 3D viewpoint, without using any ground truth viewpoint as supervision. So this is one of our first works that does viewpoint learning in a completely self-supervised way. So we learn a category specific viewpoint network. For example, given a face images, we learn a face viewpoint network, and given, let's say, car image collections, we learn a car viewpoint network. So our main the key technique that we use is that actually to close the loop with generative networks. Like, for example, given a set of images, we pass through our viewpoint network. Apart from the viewpoint prediction, we also predict style code corresponding to that image. And we pass this both viewpoint and style code through this viewpoint aware synthesis network to synthesize the image. That's how we can actually close the loop here. With these loops, we enforce some consistency losses, which we call generative consistency, which I will explain a bit more in the next slides. So let's say given an image, we pass through our viewpoint network to get the style code and the viewpoint, 3D viewpoint. And then we pass this both through the viewpoint aware synthesis network to generate an image. And we can have an image consistency loss between input image and the generated synthesized image. And on the other hand, since we have this generative model, we can actually randomly sample viewpoint and style code using a prior distribution to get a synthesized image. And then we can pass these to the viewpoint network that predicts the viewpoint and style code again. And then we can actually enforce consistency between style and viewpoint. So at a high level, on the left side, actually what we are doing is analysis by synthesis. So we are actually doing analysis of learning this viewpoint network by synthesizing the image back using synthesis network. So one of the nice things with the GANs is that, like, we can also actually do synthesis for analysis. So we can actually synthesize artificial data, which we can use to learn the viewpoint network. So we can actually do both analysis by synthesis and synthesis for analysis when you're using GANs to close the loop, as opposed to, let's say, using the renderers or some other techniques. So in addition to this generative consistency, we also use the symmetry constraints, which works like this. We pass both image and the flipped image through our viewpoint network and say that the output should be flipped according to this. Both azimuth and tilt should be flipped. And since we use the GAN generated data, the fake data, to train our viewpoint network also predicts a class score, which indicates whether the input image is fake or real. This is useful in learning the synthesis network. And so in summary, we use all these three different constraints: generative consistency, symmetry constraint, and discriminative loss functions to train our viewpoint network in a completely self-supervised manner from scratch. So for viewpoint aware synthesis network, our network is inspired from Hologan, which takes the viewpoint and style code and explicitly rotates a 3D latent code. So this explicit geometric rotation is what gives our viewpoint network the meaning of viewpoint, what we mean by viewpoint. And then it actually projects this rotated 3D code into 2D to get a synthesized image. So these are some synthesis results of faces on cars of varying azimuth. The results are far from perfect, but we find these are reasonably good enough to train a viewpoint network. And this is varying elevation synthesis results, and the synthesis results varying tilt. So in terms of quantitative evaluation, we evaluated on head pose estimation, and where we observed that this, even though our SSV, our technique, self-supervised viewpoint learning, is one of the first techniques to learn in a completely self-supervised way. To have some comparison, we actually adapted previous techniques like these part discovery or key point techniques, and also this hologram generated data to adapt to this self-supervised viewpoint learning. And we find that we get much better results with our technique compared to previously adapted techniques. And also in comparison to supervised techniques, we outperform several supervised techniques. Compared to recent supervised techniques, this last row, there is still some gap with our self-supervised viewpoint learning, which we hope to bridge in future. So there are some sample visual results where solid lines indicates our predictions and the dotted lines indicates the ground truth. And these are the quantitative results on Pascal VOC objects of cars, buses, and trains. And here again, compared to supervised techniques, our technique, the self-supervised viewpoint learning is competitive with respect to supervised techniques. These are some sample results on different object categories from the Pascal VOC and also on faces. So ours is one of the first approaches for self-supervised viewpoint learning, and it works on several object categories and performance close to even fully supervised approaches. The key techniques that we leveraged is that like we close the loop with viewpoint aware GANs, which enables this analysis by synthesis and also synthesis for analysis. In addition, we also leverage symmetry constraint, which is specific to the viewpoint task to learn viewpoints. So in conclusion, in this talk, I have talked mostly about the pattern viewpoint discovery from image collections. And we find this to be useful for high-level vision tasks such as 3D object reconstruction. And the key in to avoid degenerate solution in both these approaches is to leverage prior knowledge about the problem in the parts. It's about like concentration loss, equivariance loss, and semantic consistency. And for viewpoint, it's using the viewpoint aware generative network and symmetry constraints. So in future, we would like to work on, it will be future outlook, it would be great to work on self-supervised learning of other object attributes such as material properties or some other object attributes, just given image collections. And there is still a lot of scope for improvement even for this part segmentation, part discovery or viewpoint discovery. So that concludes my talk, and thanks, and comments and suggestions are most welcome. So shall we take questions?
Yes. Thank you, Varun. Yes. So at this point, if you have any questions, please feel free to either type them in the Q&A box, which you probably see in the bottom panel of Zoom. Alternatively, you can also try to raise your hand and I can try to unmute you so you can ask directly your question. But while you type in your questions, there are some questions that are already here, and I'm going to, Varun, I'm going to relay them to you, if that sounds good. Okay. Yeah. So there was one question with regards to whether objects are detected for these works or not, and I'll read the question out. Does the object detection get a feedback loop from part detection? For example, object detection may have been missed in some cases due to the many parts being obscured, but due to part detection, the missed objects can be redeemed?
If I understand correctly, probably this question is asking about if the object is not detected, how can we discover parts? So here there is, if that is the question, I think here actually there is some basic assumption which I did not clearly explicitly mention, which is that like we assume that the parts are the entire object is present in these images. Otherwise, it makes it very difficult to learn to discover parts. Like we already assume that all the images have almost all the face available. Like probably they are like extremely rotated. There could be some self-occlusion, but the faces are available in. So yeah, compared to existing key point works, which assume the tight bounding box around faces, we actually relax that assumption that we take, let's say, 30% of the image around faces. Yeah, so I think that's a question, I guess.
Yes. So another one is for the SCOPS work, Varun, there's a question, what is the evaluation metric? Is it similar to IOU or dice coefficient?
Yeah, so since it's a self-supervised part discovery, it is very difficult to evaluate this. So the way we evaluate this is that like actually we take the key point annotations from these ground truth data sets, let's say these faces or some Pascal data sets, and we actually take the centroid of our segmented parts and we learn a regression layer from these detected part centroids to the ground truth things with very few very few samples. So this is how we align the parts to this centroids. I mean, how well these part segmentations can predict the center, the key points, the ground truth key points. And then our metric is mostly on these key point detection accuracies. Yeah, so it's very difficult to do IOU because these self-supervised parts, there is no corresponding ground truth parts like, yeah.
I see. So there's also two questions about the segmentation basis, how they are sort of computed. Maybe you can speak a little more to the non-negative factorization.
Oh, segmentation basis. So I think the segmentation basis is mostly like these, let's see if I, so the segmentation basis are just like features that we actually learn while learning the part segmentation network. So they are just like this features, the corresponding features, which says that like actually these are like representative features for that part. Like, so this is like a 512 dimensional feature, which says that like, okay, the dominant feature for this part is this part basis feature. Does it answer the question? Like, for example, in the previous deep feature factorization, they learned this part basis using this non-negative matrix factorization. Using this non-negative matrix factorization technique where this W is the part basis, whereas in our work, we actually learn this in a feed-forward way from scratch using a neural network. So during testing, we don't need the semantic part basis during testing. During testing, this segmentation is just a feed-forward. Given an input, it gives the output.
And so there's maybe there's time for one more question. So there's also a question on the parts are hierarchical. Somebody made a comment that the parts are actually like naturally hierarchical. Then how do you determine the level of part abstraction?
Yeah, that is something we did not answer in this question. Answer in this work. Yeah, that's a very good point. That actually different objects have different number of parts. It is very difficult to say how many parts are. So in our paper, we actually experimented with a different number of parts, and we found that different object categories have different number of optimal parts. So one way to find the optimal parts is to discover this in a hierarchical way, I think, which forms an interesting future work. And also automatically finding out this number of parts, optimal number of parts for each object category is also an interesting feature. Yeah.
Okay. So Nicholas Astorga, who is one of the members of the audience, I'm going to unmute you to allow you to talk. So please, if you could ask your question since you've raised your hand. Nicholas, you're now unmuted.
I think he's still muted.
Oh. Perhaps, yes.
That might be a mistake. Nicholas said, sorry.
Oh, okay.
Yeah,
I see.
He said yes.
And
it's
then
okay.
Ademola, I can unmute you. Would you like to ask your question?
Hey.
Hey.
Can you hear me? Thank you.
Yes, we can hear you.
Thank you for that wonderful presentation. I watched your video before now, so I was ready for this session. I have the question on the part, and thank you for that beautiful answer. But then maybe I can still ask further question on that. Although you said you have not taken care of that in this work. Now, in every object, you have very number of parts, and you have answered it's difficult to determine the number of parts that you have. My further question would be, how do you segment the part? When does one part start? and end, and another start and end? That could be a question to consider. So,
Uh,
and when you have part inside part, how does the system knows which which layers of parts to fuse together as one part and start another layers of part and fuse together as another part? For instance,
uh,
in human leg, you have the leg as part of the body, but then you also have the lower limbs and the upper limbs as part of the body, but essentially it's first of all part of the leg before it is part of the body. You get that? Thank you.
yeah. Thanks for the question. Yeah, I will try to answer quickly as we are running out of time. So here we don't do this hierarchical part segmentation. So our network assumes that the part is kind of like mutually exclusive. So when it says so to actually get this part segmentation, we do some the thresholding on top of network output, which says whether it belongs to part 1 or part 2 or part 3. So there is no hierarchical nature here. So in future, it would be interesting work to actually embed this hierarchical nature into this part segmentation output. So we don't do that at the moment.
All right. Thank you, Varun, for that very insightful talk. And with that, let's move on to the next speaker. It's my great pleasure to introduce the next speaker. She is Sifei Liu. She is a senior research scientist at NVIDIA. And among many other of her interests in computer vision and machine learning, she's very much interested in learning correspondences across images as well as across the temporal domain in a self-supervised manner. And she's going to describe some really exciting work that she has done recently in this space. And please take it away, Sifei.
Okay, yeah, thank you for the introduction, Shalini. Can you guys see my screen clearly?
Yes.
Okay, thank you. So in this tutorial, I will talk about learning visual correspondence across instance and across video frames. So in this slide, I will start with the concept and talk a little bit about what is visual correspondence in computer vision, and with the common supervised task. So first, we have the classification task in relatively the highest level, where the network trying to learn image level correspondence that pins to a specific category, and we call it the category level correspondence. And to the mid-level vision, the network instead learn a pixel-wise or region-wise classification where pixels are pinned to like human-defined semantic labels. In the lowest level, we also have supervisedly learned motion where the network is able to find dense correspondence between frames. So all of these techniques learn correspondence in a supervised manner, where labels are manually annotated to associate the common properties. However, in many applications, we need to the correspondence themselves. For example, we can do the dense pixel level correspondence to reconstruct the 3D object from multi-view images. We can also track and edit video by propagating mask or texture images. So for all of this, assigning a human-defined label is not necessary. Labeling correspondence pairs is also quite impossible for this kind of large-scale dataset. So in this talk, I want to address the problem of correspondence learning without labels, or say the self-supervised manner. So to talk about the background, learning dense correspondence has a long history. So it's usually like directly or indirectly like play a core part in many applications such as 3D shape matching and also part propagation in both the 2D and 3D, and also like structure from motion from a lot of images. And also we can do the video stitching, which is quite useful for video editing. So besides introducing the core technique of correspondence, in this talk, I will also particularly introduce how to utilize this method for the 3D reconstruction. And specifically, I will introduce two aspects of learning correspondence. The first is semantic correspondence, which aims to learn the corresponding part between different instances. And also the second part, I will talk about video correspondence, which kind of densely track regions or pixels in the time domain. And after that, I will introduce two of our recent work which utilize these two self-supervised correspondence technique to perform single image 3D reconstruction, either from a collection of images or from the unlabeled videos. So since Varun had just now already introduced the details of the core part segmentation, I will directly jump into the self-supervised single view 3D reconstruction work, where we actually build on top of the scopes. I will also briefly mention that in the middle of the talk to get a brief review. So in this talk, our goal is to reconstruct the individual object into 3D meshes without any 3D shape, annotation, camera, key point, and template. So in other words, we only need a group of images of the same category, and then we can do 3D print for all of them, which is quite attractive application. And meanwhile, the method also learn a template of one category from scratch. So first, we model the instance shape as a deformable mesh. So here we use the mesh as the explicit 3D representation. And more importantly, no matter how the shape of each instance is deformed, its semantic part doesn't change. For example, whatever a bird looks like, it always has a head, neck, and back and belly. So if we take them as semantic classes, for each face of a mesh, the class label never change. And if we have a UV space which lies all the faces in a fixed order, then the semantic map on this UV space is invariant. So we can utilize such invariants to help to learn the mesh reconstruction. So this is the core idea. And here is a previous work which is most relevant to our work. The name of the work is CMR. The idea is to input an image and use a reconstruction network to disentangle the texture flow, shape, and camera. The shape is a vertex offset with respect to the predefined template. And here we use the texture flow to sample pixel values from the original RGB to obtain a texture map, and then we warp it to the shape. Along with the camera, we can render it back to the 2D plan. And after that, we compare both the silhouette and the RGB values to ground truth in order to supervise to learn the encoder. However, we know that in this work, both the template and the camera is known. According to our setting, we need to remove that. So if we directly remove both in this network, actually this is the result we actually get, which is pretty poor, as shown in the both B and C. So in this work, we try to address this problem by making use of the self-supervised part segmentation method, which called the scopes, as Varun has introduced before. And essentially, this model can learn semantic part that are consistent between different instances within a specific category. As a brief review, the scopes model is supervised with the geometry, concentration, equivariance regularization, and also a semantic consistency constraint, which is trying to perform the spatial clustering. So we note that with the self-supervised learning, each part does not need to have a specific meaning, semantic meaning, since the pixels are clustered in a data-driven manner. So go back to the self-supervised 3D reconstruction. If we do not have camera or key point, how can we resolve it? The solution is to make use of scopes which produce consistent part for all instances. Remember that we have the texture flow, which can also sample the part probability map from the 2D domain to the UV space. According to the semantic invariance, part should be consistent on the UV space. Therefore, we simply enrich all the individual sampled scopes to formulate a canonical semantic UV map, as shown here. And we found that the canonical map has much better quality than the individual ones, as it rule out the outliers and also the noises. So on top of it, we can warp the canonical map to the estimated shape and compare it back to the original part segmentation in the 2D space through the differentiable render. So the effectiveness of semantic consistency can be further explained in this example. So once we have a flying bird, it is very likely that the network output a shape and a texture that highly consistent with our silhouette and RGB values in the 2D space. However, the semantic map are totally wrong as the head is warped to the tip of the wings. So we call it the camera shape confusion. So if we warp the canonical map to the reconstructed shape and enforce the semantic consistency between these two, and then such confusion can be easily avoided. So this is the core idea. In this work, we also discover that using an existing template is not necessary since the template represents the mean shape, and we can learn the mean shape progressively by updating it from a sphere. So what we do is to learn the network and the template in an iterative way. We start from a sphere and we are grading the average shape deformation to it for every k epoch until it converges. So in this way, we can obtain a data-driven template learned from scratch. We don't need to really assume any shape prior in this work. So each time when we update the template, we use the encoder and extract the features of all training samples, and then we average it to the in the bottleneck. So this is how we come up with the updation of the template. So meanwhile, we also aggregated the canonical semantic UV map also for every case epoch, and the blue box is run like an aim step in this EM like iterative learning. So this is how we train this network. And here I will show some quantitative results. First on the bird images, where we can see that the last two images are actually paintings of bird, but we can still reconstruct it faithfully. So we also train our model on rigid objects like cars and motorcycles, and also non-rigid objects like zebras, horse, and cows. So finally, I would like to emphasize the key to learn such highly ear-posed problem. So recall that I mentioned the structure for motion, which deal with the correspondence for one particular instance among multiple views. But here we only have a collection of images with totally different instances. So the key is always to find the semantic correspondence that can associate them. So here is the semantic correspondence that we can show visualize using the scopes result. So I'd like to mention that in this work, we also trying to get back to improve the performance of the semantic core-part segmentation. So please find the details from the paper. In the next, I will talk about how to learn video correspondence, and after that, I will talk about how to use it to reconstruct the dynamic mesh in a self-supervised manner from videos. So in this work, we learn reliable dense correspondence from videos in a self-supervised manner. And given a video, the task is to learn the pixel-wise or region-wise correspondence among different frames. We treat each pixel or region as basic visual element, and we build a fully connected graph between them, where each visual element is a vertex, and the possible correspondence between them are the edges. So for each vertex, we model the correspondence by learning the probability with respect to all the possible elements being connected to it. So as a result, the probability vector can be with a length of n, indicating the number of vertices or pixels of a frame. So in total, we will have an n by n affinity matrix to model the dense correspondence in a probabilistic manner. And the element of the affinity matrix describe the similarities between two vertices. The full matrix can be used as a global filter to warp one frame or feature map to another, and alternatively, it can also be used to transform a standard coordinate map, which indicate where an object travels to in the next frame. So with the basic graph structure in this work, we propose to learn the reliable dense correspondence from videos in a self-supervised manner. And the reason we resort to the self-supervised manner is because annotating the pixel level correspondence is almost impossible. So in this work, our learning process will integrate two highly related tasks. One is the object level matching that tracks large image regions in the video, and the other is fine-grained matching, which establishes pixel-wise associations between consecutive video frames. So although these two tasks are highly correlated, they are seldomly solved together due to different optimization goals. And here we demonstrate that these two tasks benefit each other by sharing an affinity matrix that associates the content of two images. the region level localization will help to locate a patch that is similar to the reference, and the fine-grained matching further enhance the feature representation by the reconstruction loss. So since these two affinity and sub-affinity are computed from the same CNN network, so when we are learning with two tasks, they will always progressively benefit the self-supervised representation learning. As a result, we will see both the localization and the matching of pixels being continuously improved from the first iteration to the last. And specifically, given two frames, we first random crop a patch from the first frame while we keep the original second frame as the target frame. So the CNN will learn image representation output from the same CNN network. And we after that, we will compute the affinity matrix to represent the similarities between these two feature maps and know that this is a rectangular affinity matrix. So here we can multiply the affinity matrix with the standard grade coordinate matrix. And then using this formulation, we can localize the source patch in the target frame, as shown in the yellow box. And the localized patch share common content with the source patch, and we call the patch the target patch. So with the target patch, we can move to the fine-grained stage. And in this stage, the network learns to warp the color information from the source patch to the target patch. So since the target patch is a local region of the target frame, an affinity, sub-affinity matrix can be extracted accordingly. So here we can use the sub-affinity matrix to directly warp the color information from the source patch, while the difference between the predicted target patch and the ground truth patch serves as the supervision signal. So here in this framework, when instead of transforming a raw frame, we utilize a pre-trained autoencoder and we carry out the transformation in the bottleneck. And then finally, we calculate the objective by using, for example, the L1 or L2 distance between the reconstructed and the ground truth target patch. So, so with this objective, we can backpropagate the gradient flow. So we can see that the gradient flow will flow back to the sub-affinity matrix. And because this APP and AF is shared, so this gradient actually directly flow back through the rectangular affinity matrix and directly to the CNN. So we can imagine that with the CNN being improved, we will get a better localization result. And after we have a more accurate patch, we can perform better fine-grained matching in this stage. So that's how they can like progressively benefit each other. So on top of the progressive training framework, there are still existing matching ambiguities. For example, here so far we only use the frame reconstruction as the only objective. So this gives the model a lot of freedom. For example, one pixel here can be matched to any pixels with similar color. The objective itself does not regularize the local context for matching, which means we need to resort to more spatial regularizations to eliminate the mismatches. So because we carry out tracking by propagating individual pixels, and here we can propose a concentration loss, which state that once we crop a local region and transform these pixels to another frame, these pixels should stay together instead of diffuse apart spatially. So this loss will regularize that the local context should also match to each other rather than only match to the individual pixel. So once the object or local regions are moving over time, they should also move as a unit. So this is the idea of the concentration loss. And meanwhile, we also propose the orthogonal regularizations, and this is similar to the cycle consistency. Considering the orange pixel in the frame 1, we can map it to the frame 2 and then map it back to the frame 1. So here we can directly regularize that the pixels mapped back to frame 1 will be close to its original location. So mathematically, we will still make use of the affinity matrix that match features from the frame 1 to 2 and back to frame 1, where we will have this kind of formulation. So since the two frames are from the same single clip, usually we'll have the consistent style. And the style here can refer to, for example, the style transfer, the similar concept in the style transfer. So here we can describe it as an energy preservation term between these two features. And by combining these two terms, we can finally reach to an equation showing that the affinity transformation should be orthogonal. So the orthogonal constraints satisfy both the cycle consistency and the energy preservation in videos. And it also saves the computation since we can avoid the compute the affinity matrix twice, like forward and backward, as shown in this figure. So here we show the quantitative ablation studies on the task of instance mask propagation on Davis 17 using the J-mean and F-mean evaluations. So the task is to propagate a ground truth segmentation mask from the first frame to the rest, and which I will show the quantitative result later. So we found that by dropping different blocks like localization, orthogonal, and the concentration loss, the performance can decrease, will decrease constantly, which means all of these modules I have introduced so far will contribute to the video correspondence learning. So here I will show some results for the propagation of instance segmentation as I have introduced. So our method can preserve more details during the propagation process thanks to the learned dense affinity matrix and the joint training of the region and pixel level matching. So we found that the learned affinity can also handle pixel level tracking. For example, we can use it to track pose, and this tracked pose faithfully describe the motion of the human pose over time. And here is another example showing the human part propagation. So in this data set, there is actually a lot of fine-grained details like hair, the region. So we can see that the affinity can actually track these small regions faithfully with a long duration. So the learned affinity matrix or the CNN's self-supervised representation is quite general and can be used to propagate any attribute. And here I also show that we are able to propagate a random strip painting or texture on videos, which were also used in the next application. Yeah, so the next I will talk about the recent work regarding to dynamic mesh reconstruction from video in the wild. So this is actually an extension of our single image reconstruction network where we utilize the previous video correspondence learning method to move it to the video domain. So mostly existing work of dynamic mesh reconstruction rely on strong shape prior, for example, the articulated model to model the motion patterns. So for example, we have simple for the human body and 3D mobile model for dynamic face. So our model is more challenging in the sense that we do not require such prior knowledge since they may be hard to obtain for wild animals that are hard, that is not able to be scanned in controlled environment. So in this work, the goal is to reconstruct a non-rigid object instance from, for example, a video of a bird that captured in the wild. So recent work has successfully trained a reconstruction network for a single view object instance given a group of trained images that annotated with silhouette and key point. However, when we try to apply the trained image-based model to a testing video, the reconstruction object show discontinuous shape and flickering camera predictions. So the reasons are many. So first, most videos we found from the internet is captured by mobile phones. Some of them contain low quality frames or with small foreground object. Others show diverse like appearance variations such as lighting or cluster background. So almost all of them show large domain gap between the image dataset and the testing dataset from the video. So one solution is to annotate bird videos as much as possible so that we can retrain the model to cover this domain gap. However, to annotate video is still never easy. It requires extensive human label, and we cannot guarantee the coherence of the annotation. So how to deal with it? In this work, we propose an online adaptation approach to this solution. As the solution. So we first train a single view reconstruction network using a group of annotated images. And during testing, we fine-tune the network to let it always adapt into a video. So the online adaptation is also called test time training, where the difficulty is that we do not have any labels on the test dataset, the videos. We need to figure out the effective self-supervised objective that can improve the network over time. And here we resort to the temporal consistency. So in this work, we figure out several important factors with respect to shape, texture, and random part, which reveals the object's internal properties and agnostic to the shape deformation caused by the non-rigid motion. So during test time training, we enforce the predictions of all these factors to be consistent among different frames of the same from the same video clip. So for shape, instead of predicting the coordinate of the row vertices, we decompose it as shape basis combination and the offset with respect to it. The shape base are the shape clustered via KNN from a base network. And the combination of base reveals the identity of an instance. For example, it can be an ordinary bird or a duck or a flying bird. And we enforce the prediction of the coefficient, the beta here, to be always the same for different frames. So this is how the shape invariance is conducted. And likewise, we also explore such invariance over the UV space, where the independent, which is independent to the shape deformation and the camera view. We can enforce the RGB texture or appended random strips on the UV space to be consistent over frame. So in detail, we paint random strip only on the first frame and propagate them to the rest of frames using our self-supervised video correspondence learning algorithm. And after that, we map the individual part to the UV space, enrich them to have a more reliable part map, and warp it back to each predicted shape and render it back to the 2D space. So by comparing them against the original propagated strips in the 2D domain, the shape and the camera can be regularized over time. So finally, we show much more stable and temporally coherent dynamic mesh reconstruction result using the proposed method. Well, here is another example where we can see that the shape is actually much more stable over time. So in addition, we also show that compared with the image-based model, where the reconstruction is conducted per frame, our method can produce much more coherent camera and mesh evolving over time. We also tried our method on other animals in the wild without articulated models, such as to a walking zebra. So here to conclude, this work provides a way to carry out research such as 3D reconstruction to the endangered species for which like scans and other kind of ground truth labels are difficult to obtain. So the above is my talk about the details for both semantic and video correspondence, as well as their applications to single image 3D reconstruction. So in this slide, I'd like to discuss a little bit about the fundamental concern for self-supervised learning, which is how to avoid the degenerated solution. In the image-based 3D reconstruction, since we assume no shape prior, the camera shape confusion would be a typical degenerated solution for naive joint prediction. And here we avoid it by introducing the part correspondence in order to regularize the prediction. Regarding to the video correspondence learning, the degenerated solution usually appears if there is a cycle consistency loss. For example, in our orthogonal regularization, the model tracks pixels back and forth and constrain them to fall in the same location. So it's very likely that the model will learn an identity affinity matrix while the pixels always stay in the original location. So in our work, since we also have several other regularizations like reconstruction, concentration, so this degenerated solution can be easily avoided. And in several other related work using the cycle consistency for video correspondence learning, different augmentations like random cropping is applied to avoid it. So more information can be found from these two papers. And the key to model the correspondence is to learn the interframe affinity matrix, where we utilize it to link two highly correlated tasks. And for the semantic segmentation, we also trying to use it for the 3D reconstruction. So what is the next step? In this slide, I will show that very directly, we can come up with a common neural network where simultaneously output both the semantic correspondence and the video correspondence. And in this way, we can directly conduct the task on the, for example, the video-based 3D mesh reconstruction from a collection of images and videos. So this is the next step we can see. We will also leverage different tasks like semi-supervised learning or few-shot learning, along with the self-supervised regularization from images and videos as the future direction. So this is the above is my talk for today, and thank you for attending. I would like to take any questions.
All right. Thank you so much, Sifei. That was a very enlightening talk. So we have one question from the audience, and just in the interest of time, because we're running a little behind, we will try to keep the questions brief. So there's a question from Kaushik Narasimha. He asks, can't the blur, so this is with regards to the test time training piece that you described. Can't the blur in frames interfere in the learning process? Is a frame qualified for sharpness before interframe tracking?
I'm trying to understand the question. So does it mean that how to deal with the blurring of texture?
Yes, exactly. When we are trying to track across frames is the question. Do you select frames when you're learning the tracking across frames? Do you pre-select frames that are sharp and deselect the ones that are blurry?
So we do not particularly deal with that. So this will particularly introduce another like blur detection module. So we don't specifically introduce that. So for the texture part, the texture consistency, we're actually trying to use the texture swap loss, which trying to enforce the mapped texture in a UV space to be always consistent. So that kind of regularization already trying to improve the quality of the texture prediction. So I think it will simultaneously addressing the kind of blurring of the model. Yeah.
Okay, thank you. Moitreya, I'm going to unmute you so you can ask a question since you've raised your hand. Are you able to ask a question? Okay, I guess probably not. All right. In that case, in the interest of time, I would like to please thank the speaker, Sifei, for a very interesting talk. And then let's go on to the next presenter, that is Arash Wahdat. He is a senior research scientist at NVIDIA. And among his many interests is learning with imperfect labels, and in particular noisy labels. And he's done a series of very interesting works, one of which is going to be presented at ECCV as I believe it is a spotlight presentation. And he will be describing that as well. And with that, take it away, Arash.
Thanks, Shalini, for the introduction. Can you confirm that you can see my slides?
Yes, we can see your slides.
Awesome. Thank you very much. I'm just trying to, I forgot now how to, okay, I will not use that, sorry. So thanks everyone for joining this tutorial today. It's my pleasure to present in this tutorial. I'm going to talk about weakly supervised learning with noisy labels. So many of you by now know that deep learning is very data hungry. It is an old story for you. Many successful stories in deep learning has been made because of accessibility of large annotated data sets with high quality labels. You know that in many cases, collecting data can be done cheaply. You can get a lot of images easily, but collecting annotation is very costly. Sometimes you need to train annotators to do your annotation task. Sometimes you need to hire experts in a field to do the annotation. And you may need to ask multiple annotators to make sure that your annotations are high quality. So annotation costs can be reduced usually by a large margin using some cheap approaches, but usually these approaches come with some noisy labels. In fact, noisy labels is kind of unavoidable problem in practice, because no matter what we do, we can only reduce amount of noise in the labels. We cannot completely eliminate them from our training data. Many well-known data sets, such as CFAR10 and ImageNet, they contain some amount of label noise in the training data. So the idea of robust deep learning is to come up with approaches that can train deep models better from some noisy labeled data. So I'm going to talk about this in this talk. So we're going to start with a quick tour of training with noisy labels. Then I will move to learning probabilistic frameworks for learning from noisy labels. I will talk about image labeling, object segmentation, object detection, and I will continue with using contrastive learning for training deep models from text as noisy labels. And I will conclude the talk with some open questions in this area. Sorry, I don't know. Okay, I messed up the animation. So the prior work in this area can be grouped into several subcategories. In the first category, we have loss correction. The idea of loss correction is that, for example, if you want to train your model with cross-entropy loss, how can you change your loss function, training loss function, such that you can still use the same old cross-entropy loss, but train your model on top of noisy labels. The second group is called robust loss functions. And then the idea of robust loss functions is actually to come up with specific loss functions for the training task, such that they are robust against label noise. One of the early works in this area is actually very interesting. They show that mean absolute error, just L1 norm, is robust against label noise. So if you use L1 norm to train a deep model on top of noisy labels, you can show that the global solution, if you can discover on top of noisy labels, is same as the global solution you would discover using clean labels. The final group is called, the third group is called curriculum learning group. The idea of this group is to come up with a weighting mechanism for each data point during training time, such that you can reduce the contribution that each data point makes to your final loss function, and the data points that have noisy labels gets actually either eliminated or they get lower weight in the final loss function so that they don't hurt the training procedure. So at the end of the day, these methods usually boil down to finding a coefficient in front of each data point during training, such that we can reduce the contribution of the noisy instances. The fourth group is called label correction. The idea of this group is to come up with a mechanism that will allow you to correct some of the noisy labels that you have during training, so that not only you discover some better labels for your noisy labeled instances, but also you train better models using these approaches. And the final group is regularization methods. So these methods are like dropout and mix-up. They're not specifically designed for training from noisy labels. But the reason I actually put them here is that in many applications, what I've seen is that if you have noisy labels and during training, if you regularize your training, your model, you will be able to get a lot of robustness against label noise. You're going to prevent your model from overfitting to training data that contains a lot of noise. And this is one of the simplest approaches that you can use to gain robustness against label noise. So I wanted to emphasize here. Many methods that I will talk about here today falls into the fourth category, which try to correct the label as the training is happening. So in the first part of talk, I'm going to talk about the work that we published a few years ago at NeurIPS. This work considers image labeling. So we're going to consider a very simple problem of predicting a set of binary labels in an image. Think of like you use text to get some noisy labels on your images. Like let's say you have this image from internet that the user says, oh, look at my cat today is sleeping in the cooker. And then you can use this image to get some noisy labels, right? You know, there is a cat and cooker in this image, but the user doesn't mention kitchen and plant. So you don't have this information. And we know that we're going to represent this noisy label as a binary vector y, and we're going to use binary vector t to represent clean annotations that we don't have access to during training. So clean annotations T, if you forget T like it's true label, they're missing during training, and we have only access to noisy labels Y. So we're going to make assumption here about the model. We're going to assume that we're representing the joint distribution over clean and noisy labels using condition random fields. Condition random fields represent the distribution over a set of binary variables using an energy function shown on the right side. If you're not familiar with condition random fields, don't worry, we're going to get rid of this requirement soon. It's just for motivating our talk, we're going to use condition random fields. And one of the main reasons that I'm using condition random field is because using, for example, a condition random field defined over clean labels and noisy labels, we can define a distribution over true labels, given image, and noisy labels very easily. This is enabled very easily in condition random fields. And we're going to use this conditional a lot in our derivations. So if I give you a set of noisy labels and I ask you to train your model, one of the approaches that you can use to train the model is the maximum likelihood estimation method. So you basically can say that I'm going to train my parameters of model theta such that the marginal log likelihood of data under my model is maximized. And here, the marginal log likelihood measures the log probability of the noisy labels given the image. And remember that we defined the distribution over both noisy and clean labels using a joint distribution. So to form this log marginal, we have to calculate this integration or summation over all possible cases of true labels that are missing, right? So there is this intractable summation that we need to do, and this can be actually exponentially many when we're considering image labeling problem. Usually because we cannot calculate this summation easily, we use expectation maximization to train this model. So the idea is same, it tries to maximize a lower bound on this, but it gets away from like this calculating this summation explicitly. So you've probably heard of expectation maximization in your machine learning courses. Expectation maximization is a iterative procedure that iterates between expectation step and maximization step. In the expectation step, we use the model itself, P, to infer a distribution over missing labels. So this is here is the true labels that are missing given image and Y. We fix the labels to those labels inferred using the model step. And in maximization step, we calculate this expectation, where expectation is with respect to Q from the previous step, right? So you can think of like this expectation, you're sampling true labels using this distribution Q, and then you maximize log probability of the joint over noisy and true labels. So we kind of use the model itself to sample true labels, and then we update our model such that the log probability of the joint for those noisy and inferred true labels are maximized. So we use the model to infer the true labels, and then we change the model such that it gives high probability for those inferred true labels, right? So if our model makes mistakes initially, we're fitting our models to those wrong inferred true labels, right? We don't have true labels, we're using the model to infer them. And we know that if we have noisy, if we make mistakes in that inference step, we're gonna fit our model to the wrong labels. So, and we know that deep learning can do that very well. So what we notice using EM is that EM makes mistakes in the expectation step, and it maximizes the model parameters such that it predicts those wrong labels, and it never actually recovers from that. So to fix this issue of EM, what we did, we came up with regularized EM. The idea of regularized EM is that usually you may have some auxiliary source of information that can help you to infer some true labels over, infer your true labels during training. We're going to use auxiliary distribution, P-aux, to represent the distribution that is formed using the auxiliary source of information. You can think of, for example, if you're working with like image classification, you can use text to learn a relationship between noisy labels and true labels, right? So you can use that inference. So you can use this auxiliary distribution to infer true labels from noisy labels by just like doing data mining on text and stuff to get the relationships between them. I'm going to talk about how to get these auxiliary distributions. Now, if we have access to some auxiliary source of information, we're going to now define this step in the expectation step. We're going to say that Q should minimize this summation over KL, this summation with two KLs. The first KL measures distance from Q to the distribution that model forms over true labels given image and noisy labels. And the second KL measures the distance from Q to this auxiliary distribution that we get from auxiliary source of information. And the idea here is that using this minimization, Q not only should be close to this distribution formed by the model, it should be also close to the auxiliary distribution. The nice thing about this minimization is that we show that actually there is a closed form solution for this minimization, and we can obtain the closed form by using a geometric mean of this distribution and auxiliary distribution. And the nice thing about geometric mean is that the geometric mean of probability distribution corresponds to just weighted average in the log probability space. So many of you have worked with like logits in classification, like usually your networks predict logits before softmax layer. So if you want to calculate geometric mean between like two categorical distribution, this corresponds to just simply taking average between logits. So it can be implemented very easily. So in the regularized EM algorithm, we modify expectation step. In the expectation step, we use the geometric mean of the distribution that the model infers over true labels, as well as this auxiliary distribution. And there is this alpha that reweights the geometric mean. In the expectation step, we're doing the same thing as EM was doing. So remember that initially I discussed that we're going to use conditional random fields to represent a joint, but you may say that I don't want to use conditional random fields. They're like too much troublesome to implement. What if you just want to train a classification model that predicts the clean labels? So we're going to assume that your classifier just predicts the distribution over true labels given image. This is usually what we want to train, right? We actually observe that we can still use our model that we described in the previous slide. The only difference is that in the expectation step, we can just use the model itself and mix it with this auxiliary distribution to get this distribution over true labels. So this is just the output of model mixed with the auxiliary distribution. And we call this self-correcting inference because you can think of like this auxiliary distribution forms some distribution over true labels, but then the model itself tries to correct the mistakes that auxiliary distribution is making. So we're using the model to correct the labels as the training goes on. So that's why we call it self-correcting. In the expectation step, we're going to again infer the labels, true labels, using Q from the previous step, and we're going to maximize log probability of the predicted labels under our model, basically. This corresponds to just basic cross entropy loss, minimizing cross entropy loss, where Q is the soft label provided to cross entropy. So it can be done very easily using like PyTorch or TensorFlow. So the take-home message that I like you to have is that label noise is a very common problem in many applications. And if we have some auxiliary source of information, we can use that auxiliary source of information to come up with a self-correcting mechanism to infer true labels during training. And we show in this work that actually this mechanism can clean up the labels, noisy labels to very good amount, and also can give robustness against label noise during training. So in order to see how we can use this in practice, I'm going to show you one of the follow-up works that we did, and we used this model for training object segmentation models. This paper was presented this year at CVPR 2020. So semantic segmentation, it's a very challenging task. Label noise is unavoidable because of like object boundaries and the small resolution of objects. Usually it's very hard to get accurate labels. And labeling is very expensive. Like if you want to give a segmentation of this bike, in average, a study shows that it takes 8 times more than just drawing a bounding box on this bike. Or it takes 80 times more than just saying that this image contains a bicycle in it. So in this work, we're going to have a semi-supervised training setup where we have 2 sets, one small fully labeled set that contains images and bounding box on objects, as well as the segmentation map of the objects. And we have another large set, it's a weakly labeled set, where we have images and only bounding box of the objects on that set. So this is a semi-supervised setup because we don't have access to the segmentation labels in the large set. So remember that because on this weakly supervised set, we don't have segmentation masks, we need to come up with an approach to infer the segmentation mask on these images, right? So to do that, we came up with this idea of auxiliary. We need auxiliary distribution. We came up with this auxiliary segmentation model that takes image and bounding boxes, and it tries to predict segmentation map. And we know that we can train this on top of the fully labeled set, because on fully labeled set, we have images, bounding boxes, and segmentation maps. We can train this in a very easy way. So then if we have this auxiliary segmentation model, now we can use this to train a primary segmentation model that will take image and predict segmentation maps, right? If you want to train this, this can be done easily on fully labeled set. We have images and segmentation. We can just use cross-entropy loss to train it. But for weakly supervised set, now we can use our auxiliary segmentation model that takes image and bounding boxes and makes some distribution over segmentation mask. And we can use this as soft labels for training cross-entropy loss. And what happens is that we realize that if we assume this is auxiliary distribution, this corresponds to our geometric mean way of inferring the distribution over true labels. But where in this geometric mean, the coefficient is infinity. So it just only looks at the auxiliary distribution. We knew that we can do potentially better. So one way of improving this is to use the model itself, the primary model, to fix some of the mistakes that the auxiliary model is making. So we can use our geometric mean principle or geometric self-correction and combine the predictions that the primary model makes with the auxiliary distribution to come up with better segmentation. And then use that as the target on the weakly set using cross-entropy loss. In this work, we actually realized that we can also go beyond just geometric combination. We can even train a neural network to combine the output of the primary model and auxiliary model to get better distribution over true labels. So in the previous part, I talked about how we can use this model for training segmentation models. Here, I want to show you how we can use this framework for training object detections and gaining robustness against domain shift. So many of you have worked probably in computer vision. You know that domain shift is a common problem. In many applications, we train our models on a data set, and when we deploy them, because the distribution that generates data is very different, our accuracy usually drops in the real world or target domain. So this is called domain shift. And in object detections also is a very common problem where we train our models on some like available public data set, and when we deploy, because it's deployed in a different city, our detector starts making a lot of mistakes. So in this part of talk, what I'm trying to understand is whether we can use training from noisy labels as a training framework for training domain adaptive object detection models. So the way we're going to attack this problem is that we're going to assume that we have some source domain and we have some annotations on object bounding boxes on that source domain. We can use the source domain to train a faster RCN, for example, and then we can take this faster RCN and apply it to our target domain. We know this faster RCN will make mistakes because of the domain shift, right? But these bounding boxes have some accuracy. Usually they're not terrible. The accuracy usually drops, but we can think of these bounding boxes that we get on the target as bounding boxes with noisy labels. So now here comes the training from the noisy labels. We have noisy labels on the target set, and we have clean labels on the source set. Then what we do, we take all the bounding boxes extracted from the target and source, and we feed them to image classifier. Image classifier will learn to basically predict classes of each images, right? So we can think of this image classifier as an auxiliary distribution that will infer distribution over class labels of the bounding boxes, given an image and bounding box, right? And then what we can do, we can use this as auxiliary distribution and come up with a robust loss function for training faster RCN. The principle is very similar. This image classifier will help us to infer the labels over the detections on the target set. I'm not going to go to the details of this, but the idea is basically very similar to the previous part, where we're using the geometric self-correction principle to correct the misdetections on the target set. So this brings me to the final part, where I want to talk about how we can use contrastive learning for training deep learning models from text. This part of talk is based on a paper that will be presented at this ECCV 2020. Tammei is going to talk about this on Thursday. So if you're interested, or if I can get your attention, I would definitely encourage you to check Tammei's talk on Thursday. So we know that there are a lot of text and images on the web. And in fact, earlier work on weakly supervised learning, they were advertised as webly supervised vision model because the supervision was coming from web. However, in the past few years, there has been tremendous progress in unsupervised representation learning from natural languages. Like language models like BERT and GPT-3, they provide very rich representation of words and sentences in natural languages. In computer vision, there has been a huge progress in the past just 1 or 2 years in representation learning using like contrastive learning and mutual information-based objectives. So the question we were interested in here to address was that whether we can use contrastive learning to train deep models from image captions or text as noisy labels. The particular problem that we're going to consider here is weakly supervised phrase grounding. If you're not familiar with phrase grounding, the idea of phrase grounding is that you're giving an image and a caption, and your task is to find the image region that corresponds to the non-phrases in the caption. So you kind of want to localize the non-phrases in the captions in the image. And remember that we're targeting this problem in a weakly supervised setting, meaning that during training, we only have the image and caption pairs, and we don't have access to the bounding boxes. So this is the weak supervision, where we don't have the correspondence between image regions and the non-phrases. So to tackle this problem, we're going to assume that we have an object detector that we can use to detect a set of regions in image with some representation extracted from those regions. We're going to also assume that we have a language model like BERT that can help us to extract some representation or contextual representation from each word in our caption. And then to tackle this problem of matching words to regions, we're going to assume that we have an attention model, a learnable attention model, that by training the parameters of this attention model, we will learn to match words to regions. So we formulated this matching as a learnable attention model. So our key observation in this paper was that in order to estimate mutual information between a set of image regions and a set of captioned words, you need to have alignment between words and regions. So to estimate mutual information, you need to align words and regions. Because estimating mutual information is very hard in practice, it's an intractable problem. Instead of estimating mutual information, we're going to maximize a lower bound on mutual information using influence bound. And we're going to maximize this lower bound with respect to parameters of the attention model that I discussed in the previous slide. And what we observe is that by maximizing influence bound and by training the parameters of this attention model, we will learn to ground, basically, or localize words in the images. So let's see briefly how this can be done. In contrastive learning, we need to have access to a compatibility function that measures compatibility between a set of region features R and a set of contextualized word representations W. In training using contrastive learning, what we are doing, we're trying to maximize the compatibility between a pair of image region, a positive pair of image regions and contextualized word representation compared to some negative pairs. So we're trying to increase the compatibility between positive pairs compared to some negative pairs. And in order to construct negative pairs, one way is that we can take the caption and replace the image with some negative image, some image from the training data. And we can construct a lot of negative pairs by just replacing the images, right? This is one way. And we found that this is actually very effective in learning this attention model. But another way is that we can fix the image and we can start replacing the words in the caption. The simplest way will be just to randomly sample some word from our dictionary. If we randomly sample, we're going to get words like car that doesn't really fit to this caption, right? We observe in this work that, in this work, we observe that we can actually use the language model itself to find contextually plausible words that fit well to the context and also can act as very good hard negative for our application. So I'm not going to go to details, check Tammy's talk for this, but we actually discovered that the language model itself is good at discovering, for example, words like cookie that fits well into this context. That if you replace donut with cookie, it's actually a very good negative candidate for this task. So I will discuss the attention model very briefly. In attention model, we start with an object detector that extracts some set of image regions with some features extracted on those regions. And then we also assume that we have like language model like BERT that extract contextualized word representation for each non-word in our caption. Then we're gonna calculate, we're gonna use fully connected networks to extract set of keys and values for each region, as well as queries and values for each word. Then we use these query vectors on each word to form attention over all the image regions. So A represents the attention score extracted by comparing queries with keys. And then we're going to use those attention values to aggregate value features on all the regions. So we're just aggregating all the value features extracted from all the regions. And then we calculate the compatibility between the attended visual representation and the word representation using just a dot product between them. So this is our attention model. So let's see how this model works in practice. Here we're looking at the pointing accuracy as a measurement of how well we can grade on Flickr 30K entity test data set. Higher is better. And here I'm showing you how if we were using just random BERT features compared to pre-trained model, we can see that using our model, we get around like 10% improvement in phrase grounding. And then if we use just random negative words, we almost see no improvement. Like our model with only the image negative pairs is enough. Like we don't get any improvement by using random negative words. But if we use contextually plausible, like our approach for extracting contextually plausible negative words, we get around 10% improvement. These two curves, these two bars represent two different variants of our model, but it's very easy that like we get around 10% by using a BERT representation, and also 10% by using mining basically hard negatives using BERT. So the take-home message that I'd like you to have is that recent advances in natural language processing have brought us very rich representation on text using like models like BERT or GPT-3. Also, contrastive learning is also a very good framework for training models. We showed that contrastive learning can discover object locations when we maximize the lower bound on visual information. And we also showed that BERT can actually provide very rich representation and can be used to extract plausible negative words. If you're interested in this work, I definitely encourage you to check this website. We very recently released the code as well if you want to play with this framework. So to conclude this talk, I would like you to know that label noise is a very common problem in many real-world applications. In this talk, I talked about self-correction mechanism as a way of handling noisy labels. Even though this area is very important, unfortunately, there has been very small progress in this area. I think as a community, we need to focus on this area more because it has a lot of actually real-world impact on training deep models in a cheap way. Contrastive learning is an effective framework for learning from text data in a weakly supervised setup, as we saw. Also, language models provide very rich information. I think as a community, we should use them whenever we're training models on top of, for example, text as annotation. And also, I expect to see actually more in this space in the next few years in like a computer vision community. I want to also emphasize that there is a very big gap between theory and practice. Many theoretical works makes assumption about the noise model that doesn't really apply to the real world applications. As a community, we need to think about how we can come up with the new theoretical frameworks that actually provide guarantees in terms of training with noisy labels and having robustness against label noise. So I'd like to thank all the co-authors, mentors, and interns that actually their great work contributed to this talk. If you have any questions, I'm going to try to answer some of them here. If you have some other additional questions, please feel free to contact me either through email or Twitter. And I have a lot of references here, and you can find them on the PDF as well of this talk. And there are more content actually on the PDF and the video that recording that we posted before. This was a bit shorter version of that. Thanks a lot.
Great. Thank you so much, Arsh. That was a very, very interesting and insightful talk. So there are a couple of questions that came through on the Zoom channel, and so I will try to read them out to you. So one of the questions was, why do you use geometric mean in the correction step?
So the geometric mean came from some like basically a probabilistic framework, a regularized EM, that where we were saying that we actually showed that we can modify the EM training by just adding a KL term to the objective. And then we noticed that this KL, this additional term, can be actually optimized very efficiently by just geometric mean. The global solution is the geometric mean of these two distributions. But then in one of the works, as I said, we realized that, okay, geometric mean means just actually linearly combining the logits or log probabilities, but we can replace that linear operation with just convolutional neural networks that do even much better. So I think that geometric mean came from theory, and in practice, this is one of the gaps, right? Came from theory, and in practice, we realized that convolutional neural networks would do even better than geometric mean.
Interesting. There's another question. Are noisy labels related to one-shot learning?
That's actually a very good question. Are noisy labels? I don't know. I think because what I notice is that we can do semi-supervised learning with like noisy labels. We kind of formulate it as that, right? Even like domain shift can be handled. But one shot, yeah.
So I think there's some relation in the sense that if you learn with, so in one-shot learning or few-shot learning, you're most likely, your sigma or your variance on your output is going to be quite high because you learn with such low samples, right? And so I think there is some, there can certainly be some learnings from the literature on learning with noisy labels that can be applied to few-shot learning, simply because like the variance on the prediction is so high. And here also you're dealing with that issue. Right? When you're explicitly learning with noisy labels.
I was actually thinking like whether like these, like, I think the main message I had was that if you have some auxiliary source of information, you can infer labels better. And I'm wondering whether like we can use this kind of like auxiliary information to reduce that noise on the prediction task. I think actually it's interesting. I haven't seen, but it might be that there's some work in this space. It would be interesting to see if one can formulate one-shot learning using noisy labeling.
Right. So there's a very nice, interesting question. So Moitreya says, should we view this work in the line of prior work on multitask learning? If so, how sensitive is the algorithm to the choice of the auxiliary tasks? Also, can you please suggest some appropriate auxiliary tasks for videos? And I think they're referring to your earlier part of your talk.
Yeah. So, okay. So I think multitask learning definitely, like, it's related to multitask learning. I think at some point we were, with my intern, we were actually considering how we can formulate this problem as multitask learning as well. How sensitive it is to choice of auxiliary tasks. One thing that I think we observed was that, so for example, in our case, we have auxiliary tasks with this auxiliary distribution, and we realize auxiliary distribution helps a lot at the beginning of training as like guiding the model to not to make mistakes, but the slowly model itself becomes very good, so that later on we can actually rely on the model itself to infer the true labels on the noisy like labeled data. So I would say as long as your auxiliary task has some correlations with like capability of inferring true labels, that would be perfect, but it doesn't have to be a perfect correlation. Because usually what we want, initially, we want to guide our main model to infer the true labels correctly. And moving on, we can, it's like training a child. Initially makes mistakes, and slowly you make some guidance, and then it starts inferring true labels with more accuracy. So I think this is the correlation initially matters. Appropriate auxiliary tasks for videos. I think this is actually what I noticed in auxiliary distribution I was forming, actually domain knowledge was very important. Like you had to think about what is the problem you're solving, how can you incorporate some domain knowledge into this, which is the art of basically data scientist or research engineer to come up with something like this. In videos, I would say there has been a lot of work like coloring videos, for example, right, for tracking and stuff. I'm wondering if any of these can be done. Like, for example, we should think about like what is the auxiliary task that can help us infer true labels. I don't know if coloring would be one of them. Maybe because if you want to color, you need to know what are the labels. That would be a good idea. But okay, it's just I'm throwing it out just now. I don't know exactly.
So there's also a question about the phase grounding work and how the hard negatives were mined for that particular work. Do you use some nearest neighbor approach to mine hard negatives, since mining suitable hard negatives is important to training the model to prevent collapse during training? And I had a follow-up question also about the hard negatives, which was, do you also try to mine hard negatives from the image domain? I know you mentioned that you try to mine them from the textual domain.
Yeah. So regarding the first one, the way we actually did the hard negative mining is that, let's say this is your caption, right? And then the word of interest is van. So what we do, we want to replace van with another word that is contextually plausible. It fits to the context, but it doesn't correspond to van itself. So what we did, we fed this sentence to BERT, but we masked this word. And then BERT comes up with some predictions for that mask word. And we notice that those predictions usually sometimes contains the word itself, van, but it also contains other words that actually contextually fits very well, right? Then we came with a very simple re-ranking way of removing the words itself or the synonyms of the words itself, and to keep the words that actually are contextually plausible. So the basic idea was just to feed masked word to BERT, look at the output of BERT, and then just do a very simple re-ranking of the candidate words to come up with contextually plausible negative words. And it worked very, very well. We looked at a lot of examples and stuff. We noticed that the words fit well to the context. Like if you were reading the sentence, it would make sense to you, but it didn't exactly correspond to the word that we were replacing. It wasn't synonym of that word. Regarding your question, we didn't do it for images. That's actually a very interesting direction to explore, to see like how hard negative mining will help this. That's actually a very good idea.
Interesting. And there's two more questions. One of them is, can this approach be generalized to be used in object detection problem? If so, do you have some thoughts on how?
Yeah. So I think actually one of the applications of phrase grounding is, for example, pre-training for object detection. So the easiest one, I would say, you can just use this as a pre-training phase of object detectors. Remember earlier, now I'm thinking actually that earlier in one of the talks that we had object detectors and we were training it from like noisy labels. Maybe this is one of the auxiliary source of informations we can use. Maybe this is a way of pre-training the model first before doing the detection. So easiest one will be just pre-training using this. The hardest one will be, imagine you have a huge collection of images with captions. Technically, this is just doing some form of detection. Like phrase grounding is kind of detecting words, right? Then you need to associate just classes to those words to be able to, when you do the word localization, then you can just move it to a particular class localization. So I think this can be done. This can be used for object detection.
Very, very cool. And the last question is, in practice, for example, for CPC or mine, etc., in general, how do you select the samples from the originals and the joint distributions? Do you use information apart from labels?
To be honest, I think this goes back to your question as well, that for marginals, we usually just randomly sample from other, like we have usually positive pair to construct a negative pair. In our case, for example, we just randomly sample another image in the batch, right? We didn't do hard negative mining. We did, as I said, we also looked at sampling words, but we saw that it didn't improve at all. And then hard negative mining of the words helped a lot. So usually in practice, CPC, they uniformly sample from another image or another data point in the training data. I don't know if we use actually any information from labels, because we don't, like in our case, we didn't have class labels. We had words and sentences. And if Nicholas is assuming that maybe the captions are labels, yes, we didn't try to replace the whole caption. We tried to replace just words from that caption. So maybe that means using the information from labels.
All right. All right. With that, we would like to thank the speaker, Arsh, for staying extra, and for all of you who stayed beyond 7 o'clock. And with that, we would like to conclude the first session of this tutorial. And I'd like to remind you that we will rejoin the next session of this tutorial that has 3 other talks tomorrow morning, which is going to be at 6:30 a.m. Pacific time. And you can find the converter to your particular time zone by going to the tutorials website. And I hope you have a good rest of whatever day or night, wherever in the world you are. And I hope to see you tomorrow bright and early. Thank you.
Thanks a lot.
Thank you. Bye-bye.